Good morning, everybody. This paper is Cochlear signal processing. It's a platform that we have developed at University of New South Wales, Sydney, for learning the fundamentals of DSP. It's mainly Cochlear signal processing. We model the cochlear using digital filters as a major project. The contents of the paper is going to be, I'll just introduce how we teach DSP, and then the major project that they do as part of the course is the Cochlear signal processing project. And they look at the structure of the projects will be the biological context and also linear filter modeling. And then I'll give you some of the summary of the students' response and give you some conclusion. So if you take a DSP course, a fundamental course, you will find that these are some of the contents that you'll be teaching in your fundamental course. Sampling theorem, discrete time, linear time invariant system, multi-rate systems. And typically it's a one semester course, around 50 hours altogether. That includes lectures, tutorials, laboratories. It could be run on a face-to-face or flipped mode, all sort of mode we have trialed this out. And most of the time lectures, tutorial, laboratories, but they're all, many of them are in flip mode as well. So the teaching methodology has evolved, looking back 1970 up to now. It still use analytical concepts, and students need to understand deriving theories, deriving equation, and doing some proof and understanding. But then early 80s, you had DSP chip implementation available, and then numerical simulation software has become made available to students and staff, and MATLAB is one of the examples, and then interactive visualization tools, and then project-based learning started around somewhere here, and we are now using project-based learning for DSP. And again, everything needs to be fitted in 50 hours. So one of the things at UNSW, when we were teaching DSP, one observation is that we have to make sure that after we're taught, the students actually retain the knowledge when they go to the follow-on course. That's true always, but sometimes students don't have enough fundamental learned thoroughly before they take the next course. So we want to make sure, how do you do that? We want to know that if they are actually involved in engaged in group learning, or if they get interested in a major project, they learn more about the signal processing concepts. And that actually helps them. The second problem we have is that nowadays quantum computing, artificial intelligence are two major areas where students want to specialize and do projects. But we want to make sure they do DSP project. We come up with a project such that they then continue for the thesis work as well as for PhD. So it's just to get their interest in DSP is a major challenge. But this project has actually helped us for the students to take on more DSP courses and also do higher studies in DSP. So the goals were, we want to have a single project which has got all aspects of DSP that we are teaching. So in the project, initially we will just explain them, just give them a description of the biological peripheral auditory system, what it is. And then we will explain bandpass filter models of outer ear, middle ear, and they have to implement all of them. Then we introduce the model to inner ear, how the cochlear works. And then we explain how the cochlear, the basilar membrane, the movement is translated into a neural impulses, how does it work. So it's really three parts that they have to concentrate in. The students will implement three models, and then at the end they will have a face-to-face assessment where they will explain their models, and then they will validate the implementation as well. Now we will asking them to change their code. We'll give them some ideas or modify a code based on this particular question, and they need to do on the line, on the fly. They have to do that for us. That's how we know they have actually spent time in writing the code they have understood. So if we map our curriculum into this project, the first part, outer middle ear, covers these four sections, and then the inner ear model basically cover the implementations, all these sections in the DSP course, and then inner ear cell model, mainly a little bit of nonlinearity comes into play, rectification, followed by downsampling, which is the multi-rate processing that we do, and input signals at 48 kilohertz, the output is at about 50 hertz or 60 hertz, and they need to know how to do the downsampling, and this project provides that, all those opportunities for that. And we start with initially about introduction to human auditory system. Mainly, we want them to understand the simple soft sound against a very loud sound, and how the cochlea compresses all of them. Just give them some insight to it, and then we just explain to them there are three parts: outer ear, middle ear, inner ear. Inner ear is a spectrum analyzer, middle ear is a kind of an amplifier, impedance matcher, and the outer ear is a broad bandpass filter resonating around 3 kilohertz. And they implement, then we give them the characteristics, we give these characteristics to them roughly. The outer ear looks like this, and the middle ear that, combined is something like that, around 3 kilohertz. And the students will then use a pole zero plot and approximately get this particular graph. It won't be exactly same, but at least some of clever students will get them, others will get roughly a bandpass filter. That's using pole zero placement. Once they have done that, then that's the first part. Then we explain about basilar membrane. Basilar membrane, the cochlea, if you uncoil them, it looks like this, and this is two parts separated by a membrane. It's a resonant membrane, and that position is sensitive to 20 kilohertz, and that position is sensitive to about 50 hertz. That's cochlea. So this membrane is sensitive. So we explain to them, if you give a frequency of about 1 kilohertz, and the signal travels, and the position where it's 1 kilohertz, it vibrates, and then the fluid does not travel. That's shown here as well. You can see the traveling wave of the membrane. When this is vibrating at 1 kilohertz, the traveling wave travels and make a resonance at that point, and then the wave does not travel at all. That means later on, the pressure difference here is zero. They need to demonstrate that in a picture once they have done the model. And then we explain to them for a high frequency, only that part resonates. Then we explain to them then a cochlear model can be implemented using many bandpass filters. That's the principle we kind of introduce to them first. Then we take a simple section of the cochlea. Cochlea, if you look at it, at the basal end, it is very narrow, and the apical end, it's wider. So it's like a trapezium. And we explain to them, take a small segment of cochlea, it's separated by, that's the membrane, sorry, membrane separated by two liquid. So the fluid mass is inductor, and the resonance property is LCR circuit, and we put them as one section. So if you have got many sections, they're cascaded, they're coupled by the liquid. So this is section 1, section 2, and it becomes a circuit theory. And at the end of the cochlea, there's a hole there that's purely liquid, so that will be called helicotroma. So that's modeled by inductor. So you could analyze the circuit analysis at piecewise on this one, but we don't want them to do that one. We want them to get transfer function and do it in digital filter mode. So we will then explain to them how this loading affects this section, and we derive the transfer function, which comes as the next section for you. And the voltage transfer function. If you look at the transfer function, this is the voltage. This is the pressure transfer function, that divided by that, and this voltage divided by that one is the membrane displacement. So they write the transfer function, they'll have a low pass filter and a resonant pole and resonant zero. That's for the pressure transfer function, and for membrane transfer function, these two will be there. And we can demonstrate that one. They are given these equations as well. They've been explained what they are, what the parameters are, bandwidth and everything. And then they go, and we want them to maintain the impulse response. We have got some measurements of impulse response from actual cochlea. Here, it's been measured previously in chinchilla and various school monkeys. We got some examples of them. So we tell them, we want this model to be using impulse invariant transformation, translate your analog design into a digital design. They'll come up with these two equations. They have the equation for writing all these and find the values of the coefficients. And that's all done by the students, and they'll have all the values. And then the next part is then we need to create a transmission line model. So we got one section, we know what it looks like, and when you translate the one section, it's a low pass filter, it's a resonant filter, and this is a resonant zero. So you've got a real pole, complex pole, and a complex zero. And that's input, that's the pressure output, that's the membrane displacement. So this is one section. So if you can think of it as section 1 is a filter, this is the middle ear, and then this is the ith section, this is the end section. So we asked the students, the cochlear length is 3.5 centimeter. We want them to implement 128 filters. So 3.5 divided by 128 is the one section length. So there will be, this will be 128 filter. This is your first filter. And the output of the filter is the membrane displacement, as I explained to you. So they would have 1, 2, so on, 128 output for one input. For if you have one input, you got 128 output. So you give a sine waveform here and observe the output, right? So that's what they will do. So if they cascade them, you will find they have a first filter as a low pass, resonant filter, and a notch filter. That's filter 1. Displacement is here, then pressure output, that's at that point, is connected to the next section, and so on. They've got 128 sections of that. Now the next part is that we showed you when the signal travels, then so if you take the example, the medium frequency when you give at the eardrum, when it travels, the signal travels and causes vibration at that position only. And that's somewhere in the center. So there are hair cells sitting in there on the top. You can look at the anatomy of it. That's translated here now. So if you look at that, it's hair cells sitting there and picks up this movement. So when this move upwards, this hair, the hair of the hair cells bend in one direction, and the movement of that is proportional to the signal amplitude. So if it bends more, then this amplitude will be higher. Right, so they need to model this one. So bending, and then when this come back to normal, this comes straight. So it's like one direction bending and then coming back. So we need to have some sort of a rectifier because it's only one direction. Then it's bending and then coming back is a modulation. That's like a charging a capacitor, then discharging it, charging a capacitor, discharging it. So you'll have a RC circuit there. And we also know between these points they are spatially coupled, and we need to introduce a spatial coupling. So spatial coupling is here actually, and details on the paper you can have a look. So this is the hair cell model. Once they have done the hair cell model, they are ready. That they've got all these sections ready. Now we give them the parameters. They've understood now. They need to do implementation. So we give them the design criteria. We tell them how they should be. The zero should be higher than the pole, and the Q value of the resonant filters, and the Q value of the complex zeros, and we give them all these details. We tell them to implement 128 filter, give a sine input, give an impulse, and look at the output. So here are some of the examples they'll show you. So here's the filter. They will show you some of the results. They have implemented this digital filters. 120 of them cascaded, and they say, okay, they're giving a signal of 2 kilohertz. So somewhere 2 kilohertz. So I want them to tell me what the pressure look like at 2 kilohertz. If the input is at 2 kilohertz, and they locate the filter which corresponds to 2 kilohertz, and you will find the pressure initially is high and it decays to zero at that point, because the wave can't travel anywhere. They will impose many of these waveforms in many time instant, and they will demonstrate this pressure waveform envelope. And then we say, give a sine wave, just same thing. In this case, we give sine wave of 1 kilohertz. And this is filter number, and that's the membrane displacement. You can see the membrane vibrates kind of that, and 1 kilohertz, it goes heavy vibration and it does not travel any further. If it travels, that's transient. But this is without fluid coupling. 2 sections are not coupled. As soon as we do the spatial differentiation, you will see this become like that. It's very sharp. And also we'll ask them the frequency response of that particular filter. That means if they are looking at 81 filter, the signal travels through all the previous 80 filters, and what will be look like an 81 filter. That's the frequency response. You can see because it's traveling through many filters, it gives you a really sharp cutoff, more than 200 dB per 200 dB per decade. You can get them, and it's pretty sharp filters. Right, and we check all of these when the students have done it. We make changes to them, and now looking at some of the responses, you'll find the students are saying, it gives improved their understanding, and their MATLAB knowledge has increased, and and how an analog system is modeled into digital, they've understood. This is just one particular year. There are other years also similar. These all have gone upwards, this last year as well. So we run this project as a cascaded filter. Most recently we ran as a parallel filter as well. So to give them a really good knowledge of, get them really interested. So in conclusion, a digital model of a biological system with many parameters and approximation to understand, that's what we give them. So we give them variation to students as well, so different Q values and everything. And it covers almost every basic DSP concept that we teach in the DSP course. So students are very interested in the project because it's related to human cochlear, how it does the spectral analysis. And then good students are able to stretch, and some of the students we'll ask them to make the filter adaptive as well. So they can do them. That is an extra work we give to them. And the weaker students are still say that this project gave them a good knowledge of DSP. Without this, they would have struggled to understand their actual concepts. So it is a project for students on the both spectrum. So low end, and because our students are roughly 250 students in a class, a large class. So we give them this project to help them. The students who are really good students want to do further, we give them the adaptive part of it, so they can adapt the frequency characteristics of the filters every 5 milliseconds, every 10 milliseconds. That's basically the questions, and the paper gives you more explanation, and we can't go through everything here, but if you have a question you can ask us. Thank you for listening. Thank you.